how many sig figs? 2. Oh, perfect. Okay. So this, actually, I'm going to bring out my calculator and I'm going to show you why this is the way it is. Because sometimes students will have a question about this. I'm pretty sure if I take 13.94 divided by 1.8, I get a different number. 0.94 divided by 1.8. Rounded to 2 sig figs, I'm going to put 7.7. That's a terrific answer. And I'll tell you why 7.9 is also a terrific answer. Some of you may already know. Okay, so you're like, how, Mrs. Snipes, can you have 2 terrific answers for the same problem? And here's the answer. What I did to get this was to use the unrounded version of this.
Yep.
Okay? You totally can do that. It's going to be up to me to follow your work to see which way you've done it. This is kind of a weird example where it's just totally extreme. If you round the volume before you plug it into density, you're going to get 7.7. If you don't round the volume, just kind of, you know how your calculators have that store feature? Okay, if you just store it in your calculator, you are going to get 7.9. They're both terrific. Okay? I will say, and maybe intuitively, you guys already know this, if this is using the unrounded volume, okay? If you do use the unrounded volume, the answer is a little bit stronger. Okay, but the advantage, quite frankly, to using this one, using the rounded value, is that you're less likely to round it incorrectly. Are there any questions about that? Okay. So one of the things for your homework and your unit exams, which are more important than your homework, but when it comes time to work a problem on your test, I will always say include all units, show all work, use what we call the factor label method, okay? Show all your work for your test. Do that for your homework too. Units can really help you find your way through a problem, okay? All right, so density of water, let's take a look at it. Actually, this is one of the things you need to memorize. You know how a few slides ago I put an arrow next to things to memorize? You need to memorize the density of H2O at 4 degrees Celsius, okay, with 3 significant figures is 1.00 grams in 1 milliliter. So memorize that. It's kind of a nice round number to memorize, right? So memorize that. So let's take a look at the density of water. So let's kind of orient yourself for this density. Density is along the y-axis, okay? Temperature is along the x-axis. Notice that this is colder. This is warmer. I wouldn't say 10 degrees Celsius is necessarily hot, okay? But we know the transition temperature for water, the tipping point for water under normal atmospheric pressures is 0, right? It freezes at 0, it melts at 0 degrees Celsius. So starting with water in its solid phase, okay, notice that it's the exact trend we talked about. The way you read this is as you get colder, density goes up. That's exactly what we talked about. As you get colder, density increases. Right? Here's one thing, and I'm going to show you the rest of the curve, but what's the density of water at 4 degrees? 1. Exactly. So up there is the density of water in its liquid state. Density H2O, comma, 4 degrees Celsius. Is 1.00 grams per milliliter. All right. Well, here is the rest of the curve. This over here up in this quadrant 1, right? No. Anyway, I don't know what quadrant it is. But this over here, this red part over here, is liquid water. It's funny how when we say water, we always mean liquid water. Okay, so this is liquid water. Notice what we have going on. I want you to focus on this part of the curve first. By the way, this tipping point is at a temperature of 4 degrees Celsius. We'll call that segment A. Focus on segment A. So segment A says, for liquid water, as you get colder, okay, the density increases. As you get colder, it gets more and more dense. They're about the transition temperature. Before the transition temperature, those cute little water molecules start to get ready to make those intermolecular bonds, forming that crystalline solid we call ice. Okay? And it starts to, basically the density goes down. The density goes down. It starts what I call fluff out. Okay, from liquid to a solid, it totally fluffs out. Okay, crazy. And we get this jump, this crazy decrease when it goes from being a liquid to being a solid. Is that not bizarre or what? So ice is a lot less dense. Ice is less dense than liquid water. Ice is less dense than liquid water. That means actually ice, that's why your ice cubes float, right? But that has like global consequences. We here could not exist on Earth as we are if ice or if water in its solid state were heavier, like most substances. Most substances don't fluff out like that. You transition from a liquid to a solid and it keeps getting more and more dense. Okay? I have a globe over there, but think of your ice sheets, okay? That if those actually did not float on the oceans but instead sank, they would displace all of that liquid water. Just basically would not have any, our sea levels would be just terrible. We would be water world. Okay. There is one thing about it, though. The formula for water, I know this is not anything, but the formula for water, of course, it's got 2 hydrogens and 1 oxygen. Formula for water, right? If instead of normal hydrogen, which is what this H represents, if instead of normal hydrogen you got that fancy hydrogen called deuterium, D2O is also water. D standing for deuterium, which is just another, what we call a form of hydrogen, another isotope of hydrogen. That will sink. Ice cubes made of that will actually sink in liquid normal water. So that's a thought. Makes you want to go out and get some, they call that heavy water. Okay, and it really is heavy water. Okay, I digress. So these are actually points on the graph that we just saw. Notice that we have that ever important density at 4 degrees Celsius. Okay, I told you to memorize it as 1.00 grams per mil. And if you go ahead and truncate this to 3 sig figs, okay, that's what you get. Right? You would round this 9 up to 10, then it bumps that up to 10, and that's like 1.00. So that's where that comes from. But these numbers go along with the previous graph. Okay, so density is how squished matter is together. So got a couple of objects here, and they're supposed to be similar volumes. It's like, if somebody covered your hand so you could not feel texture, and they said, I've got equal volumes of a rock and styrofoam, just based upon how massive, the hand holding your rock was, you're like, well, if density is a ratio of mass to volume, okay, they have the same volume, Okay, but for sure, their masses are not the same. The mass of the rock is a lot more. So this is kind of showing you this is a mixture. It is a heterogeneous mixture, right, of rock, water, and styrofoam. So we would say that this is the most dense. You know, we can already, just by picture, know that this is the most dense. This is the least dense. And this is the moderately dense, just by looking at what floats where. Picture's worth 1,000 words. So switching gears now to another type of problem. Weight percent is used to describe a component in a mixture. Remember, mixtures are just things that are physically combined together. So you can actually come up with the weight percent for each component. So once somebody has told you weight percent, percent means parts per 100. Specifically, this is kind of the definition of weight percent. Okay, it means that you have X grams of your component of interest, component A, per 100 grams of mixture. This is actually how you use this to unpack, what I call unpack weight percents. This next one, though, is how you calculate weight percents. Okay, so use to calculate weight percents. So basically, you'll have a mixture, you'll get the mass of the mixture. One way or the other, you'll get the mass of the component. You divide the mass of the component by the total mass, and to get parts per 100, you have to multiply by 100%. And that's it. Okay, that's your weight percent or mass percent of your component of interest. Mass fraction of a component in a mixture is very similar to weight percent, but you don't multiply by 100%. So if you compare this little formula with the formula before, what's missing is the end times 100%. Otherwise, it's the same thing. So this I've added. If you want to, underneath your your little slide, add this. You can. Okay. If you know your mass fraction, you are just a tiny jump away. If you know your mass fraction, from going ahead and knocking out your weight percent, and we're going to do a problem like that here in a minute. So all you got to do, if you know your mass fraction, is multiply it by 100%. Then you know your weight percent. Bada boom, you're done. So let's do a problem. Sometimes in chemistry or in physical science problems, I think it's helpful to draw a picture. I make a pretty mean beaker, if I do say so myself. Okay, so there's my beaker, and the problem explains that we've added 5.42 grams of sucrose. So since it's your problem and your doodle, you can make it however you want to. So I'm going to abbreviate sucrose as SUCC. 5.42 grams of sucrose. The problem goes on to say that there is 28.72 grams of water. I'll go ahead and put H2O for water. You can write out, it's your problem. And then we're supposed to do two things. So oftentimes in physical science problems, they ask you to do more than one thing. We're supposed to knock out the mass fraction of sucrose and the mass percent of sucrose here. Okay, so we can do that. Basically, what you're going to see on the next slide is I'm going to take that mass of sucrose and divide it by the mass of these two combined together in the denominator. Does that make sense? The total mass. So it kind of looks like this. Okay, the total mass of the solution would be the two masses added together. Now we do a lot more multiplication and division in chemistry. Then we do addition like this. But this is important to remember our discussion Monday. That remember, since we're adding, we're going to round according to, what do you think? Is it sig figs or decimals? It is decimals, exactly. 2 decimals. So actually the total mass that's going to go in the denominator is that 34.14 grams. Okay? So here we go. Mass fraction is the mass of the sucrose, 5.42 grams, divided by the total mass, 34.14 grams. Sometimes students will ask the good question. They'll say, well, could I have just simply taken these and put them down in the denominator? And the answer is yes. You do need to kind of, like your homework you handed in today, you do need to kind of keep your wits about you as far as rounding then. Did I collect your homework? Okay, thanks. Okay, so now the last thing we need to divide. So fingers, please. How many sig figs? Yep, I'm liking it. I've never had a student that was like missing a digit. I'd have to change how I asked that question, wouldn't I? So, yeah. Okay, so the mass fraction is 0.159. Now I'm all about units here and units in the answer. Units as you work the problem, okay? And actually, even though the top grams are grams of sucrose, the bottom grams are grams of solution, in this sort of problem, those both will cancel out. This actually is what we call unitless. It's one of the properties that's unitless. Are we good with that? Okay, so it's understood that if somebody simply told you, I have a sugar solution that it has a mass fraction of 0.159, you should be able to, this is my famous unpacking, you should be able to unpack that. This is the unpacked version. What that means, what 0.159 mass fraction means, is in 1 gram of solution, total solution, there are 0.159 grams of sucrose. So you're going to want to be able to unpack that. All right, so I added a little bit to this slide. So the second part, remember there's 2 parts to this question, mass fraction, which we came up 0.159, and mass percent for the same solution. So remember I had you write down mass percent is equal to mass fraction times 100%. So bada boom. You know, we could go to the mass percent for the same solution is 0.159 times 100%, 15.9%. Now, if somebody says that they have a sucrose solution of sucrose and water that's 15.9% by mass sucrose, this is what they mean. And you're going to want to be able to unpack that. They mean that in 100 grams of solution, there are 15.9 grams of sucrose. We good with all that? Okay. So these will be due on Friday. I smile Friday already. Oh my gosh. I do want to, and I'm going to show you what these are, but before I show you what these are, I want to do just a few slides in part 3, and I'll show you why. So these will be due on Friday. So on to part 3. Notice, by the way, the instructions say show all work. All conversions must be done using factor label. That's why I want to show you a little bit of factor label in part 3. Make sure that you round according to the right number of significant figures. So here's part 3. Part 4, excuse me, part 4.
Is that a grasshopper on that leaf?
I think so.
That is awesome.
Part 4, not part 3. Okay. So part 4, just a few slides, not to an assignment slide. Because this idea of factor label is going to help you work the questions better at the end of part 3, help you better work on them. So there were a few of these you need to commit to memory within the metric system. You need to know milli, centi, kilo, kilo, and micro. Okay, kilo, of course, is 1,000 times. And then we have the smaller than the base unit, 1/100th for centi, 1/1000th for milli, and 1/1,000,000th for micro. All right. So only one of these do you need to memorize. The first one, right? Memorize that one. Okay. These other, I might keep them handy because we'll be using them probably on Friday for working problems. Memorize it, right? This is within the metric system with regard to volume. You guys told me it's a 1-to-1 relationship between milliliters and cubic centimeters. That, by the way, is what we call an equality. Does it look like an equality? It has an equal sign, equal quantities on either side. Okay, so the factor label method of working problems is important to all chemistry problems. It's in here, all physical science problems, really. First off, it's kind of that you always use units, whether it's grams or liters or meters, always use units. Okay? No naked numbers. Okay? So remember a minute ago we had 1 milliliter is exactly equal to 1 cubic centimeter? Okay, that's an equality. You are going to use those equalities, okay, as conversion factors. That basically you're going to, and if in between is an equal sign, you're going to make ratios out of them. So I'm going to go like this, put one over the other, okay, make a ratio, or I'm going to go like this. You can actually get 2 ratios. In this case, I put this in the numerator, this in the denominator. Okay, in this case, I put this in the numerator and this in the denominator. They're different. They are what? The inverse of each other, though. Okay? So you are going to take an equality statement, make a conversion factor. I'll show you how you use those to your benefit. Okay? And with that equality, or sorry, with that conversion factor, you are going to strategically place it in your problem to get the units that you want to be left with based upon the units you start with. I'll show you an example. All right. So, for instance, if you have 2.5 feet, I could ask you how many inches. You figure 12 inches in a foot. So in 2 feet, you have 24 inches. Another 6 inches for the half a feet. So 24 plus 6, you have 30 inches. Right? 30 inches, that's it. And we're going to take that example of taking 2.5 feet, seeing what we get 30 inches, and we're going to apply the factor label method. Okay? So, here we go. First off, in order to get from, I'll show you how you kind of think through these. If you have 2.5 feet, and we kind of write them almost like chemical reactions or almost like a sentence, you're going to go from left to right. So we're going to go from 2.5 feet to question mark inches. Okay? How many inches, question mark inches, are there in 2.5 feet? So that's kind of the process of what we're going to do. So in order to get from point A to point B, okay, we need to come up with an equality that gets us there. So you guys would probably tell me that 1 foot is exactly equal to 12 inches. And you'd be right. That's the equality we're going to use. You pick your equality based upon what you need to achieve. In this case, we're going from feet to inches. Now, I'm going to show you how you get those conversion factors, those ratios. How do those work? Well, we know in algebra that as long as we do the same thing to both sides of the equal sign, that's fair game. So let's just go ahead and divide both sides. Okay, let's divide both sides by 1 foot. 12 inches divided by 1 foot, 1 foot divided by 1 foot. So that probably works. And of course, 1 foot over 1 foot is 1, exactly. And according to According to, I don't know which, the unity property, the unitive multiplicative property of the value of 1, you can stick 1 anywhere when you're multiplying numbers together, and you do not change the number. So that's to say that we can insert this ratio anywhere as we're working problems, and we have not changed the number. Okay, exactly. So what if now we do, basically we're going to end up with the inverse. What if instead of dividing by 1 foot, what if we divided by 12 inches, both sides? Okay. In this case, of course, 12 inches over 12 inches goes to 1. Okay. So do you see where we have two ratios that came from one equality statement, equivalency statement, and they both are equal to the number 1. So sometimes I'll tell students, so you have an option of using ratio number A or ratio number B. Okay, it depends on which one you pick. You're going to strategically pick it so that the units, you're going to write your problem from left to right. The units that you want to cancel or convert, cancel. And you're left with the units you want to be left with. So it looks like this. So in this problem, I usually start from left to right. I usually put the thing, what I call specific to the problem, the thing we're trying to convert, which is 2.5 feet. I usually put that over 1 to emphasize that units of feet are in the numerator. So looking back at the previous slide, call the first ratio ratio A, the second ratio ratio B. How many people think we're going to use ratio A to make feet cancel? How many people think we're going to use ratio B to make feet cancel? How many people aren't quite sure what I was after? Okay. Yeah. So if we use that one, I know I couldn't remember which is which either. If we use this one, this is actually the number 1. And using it this way, remember I said the first day you just need to, the algebra, that's what I want you to be able to recognize, that if you have things in the numerator and the denominator, those things will cancel. If you have a string of things that are multiplied by each other. So we have units of inches, and we're done. So on your calculator, if you take 2.5 times 12, your calculator will display the number 30. But now here's where you need to think smarter than your calculator. Okay, and realize that there's some uncertainty in 2.5 feet. So we need to round according to two significant figures. Okay, this, by the way, this relationship, the 12 and the 1, that brings no uncertainty. Why? It's exact. Why? Because it's by definition. So we are limited to two significant figures. You can show two significant figures two ways. In this way, you can actually, if you explicitly put the decimal, you have shown that this 0 is significant. Alternatively, that's my little check mark. Alternatively, you could pack it up in scientific notation. But that's it. That's your first kind of look at using the factor label method. Just for kicks down here at the bottom, what I've done is to take the other ratio, okay, and notice that using the other ratio, I get what? Feet squared per inches. So that's where I said that the units kind of let you know if you got it right or not. So let's take a quick look, and I will go ahead and push these out to the Twitter feed, the Donald. So these are the problems that are due. Okay, 47 and 48 look like this. You're given the volume and you're given the mass. One of the catches here, it's been a while since I did this. Okay, one of the catches here is you're supposed to get density in terms of grams per milliliter. And notice that the catch then is the volume is in liters instead of milliliters. So you already get your first chance at what I say, kind of cleaning up those units of liters. If I were just to plug in the mass and the volume like I do here, notice that I would get my answers in grams per liter. Okay, but I'm supposed to get it in grams per milliliter. If I introduce one more term, okay, 1 liter over 1,000 milliliters, notice the beauty here. This is kind of what we did before. I got this 1 liter over 1,000 milliliters. From an equality, 1 liter is equal to 1,000 milliliters. I put 1,000 milliliters in the bottom because I want milliliters. Sorry, I put liters in the top because I want the liters to cancel on the bottom of the first term. And that'll do it for you. So I'll post this. For the second problem, it's kind of similar. And the catch here, again, you need to clean it up from liters to milliliters, but you also need to clean it up from kilograms to grams. So kind of showed you that. I went ahead and gave you the 2 equivalency statements. For the other 2, it looks like this. Percent problems, sometimes it's hard to kind of show your work according to the way they should be shown. In the first problem, it goes ahead and it gives you the students. 7 students got A's, 22 students got B's, 37 students, etc. And you're supposed to come up with a grade percent for each percent of students that earn each grade. That shouldn't be too hard. I think you'll be fine there. For 64, it's a little more interesting. They say there are 84 students, then they give you the percentage that got A's, B's, C's, D's, and F's. I gave you the pattern to actually unpack those percent. So what I would do, what I'd like to see you do, is when it says 18% of students received A's, I would like you to unpack that. 18 A's in 100 students. Okay, so I'm already telling you kind of the pattern I'd like to see it. So with that in mind, do you see where if we start with the first term, 84 students over 1, okay, then we can introduce 18 A's per 100 students. Units of students will cancel. We're left with units of A's. So who in here can see my Twitter feed-ish, either through eCompanion or through Twitter? Hands. No, yes, no, yes. No? Okay, because it's really, I think it can be helpful, especially as we get, the problems get even harder. Or, they're not hard. That they get more interesting. So let me know. Actually, you guys probably already know this, but on campus there's all sorts of computers. Feel free to just, go on up to one. And they're open late. Not that you guys want to be out late, but I think they're open till like 9. So it's kind of quiet around here. That's a possibility. Okay, let me know if you have any questions. See you tomorrow. Don't forget your pre-lab. And I tried to record today's